Hello everyone, welcome back to Trans. In today's video, we are going to take a deep dive into data structures and code out a single linked list. If you are familiar with the channel, we do a lot of coding challenges from lead code, React challenges, data structures and algorithms. And while solving linked lists, it's noticed that a common gap is understanding some of what these data structures even are. Stacks, queues, graph, trees. There's that gap in knowing what these data structures is. And the aim is that we understand what this data structure is, and from there it gives a base from which we can solve more linked list algorithm questions in lead code. If you're new here, like I mentioned, we do lots of algorithm videos here and also some front-end development coding. So don't forget to hit that subscribe button, click the bell icon if this is your cup of tea. Now let's jump right into the video for today. So we're building a singly linked list. However, to understand a singly linked list, we need to understand what a linked list is. So what is a linked list? A linked list is a data structure that is a collection of nodes all connected by a link. So essentially, in a linked list, there is a node, the node has a value, and the value is linked to other nodes in the linked list system via a link. So that is the connection. Why does a linked list exist? So the linked list is a data structure that exists to manage the limitations of an array. Another reason the linked list exists is because of insertion and deleting operation. For instance, we have our array and we want to insert another value just after 3. So we are going to have to traverse, then break off this part and insert and change the what for the index change of each of these values, because now the index is going to shift and rearrange somehow, because we know that index is the primary way through which we are able to access values in our array. So the index is going to shift the resorting and all of those stuff. However, it is much more simpler to simply insert in our linked list because we are using these links. All we have to do is break off a link and point it to some other number and ensure that we want to point the link, because every node has a value and a link. So for every insertion, we are pointing a link to a new node and ensuring that we point our new node back to what already exists. So we're simply updating links. It is much more efficient to manage than the index system. And also this also applies to deletion, because if we want to delete 3, for instance, it's as easy as breaking off the link to 3 and then we simply connect 2 to 4. Whereas if we had to delete not the first or last value in an array, but maybe the 15th index, now it is much more complex, because not only are you traversing, we are also we also have to make sure to update the index of every of these elements in our array. Now it might seem like a little bit easy to do, like yeah, it's just popping something off or traversing and slicing. However, when you think about it as an index based system, when you think about it under the hood, what the computer actually has to do to updates the index of every element after deletion, shift, and all of those things, you come to see that a linked list is much more simpler to implement for operations that involve insertion and deletion, especially in very, very, very large computations. Now, a practical example of this. A practical example of a linked list operation is our music playlist management, especially if you use something like a playlist actually. A playlist is a good example of this. So you have all of your music and you decide to remove, let's say, the fourth music, for instance, and you just easily remove it and everything stays in position. There is no reordering, there is no sorting, everything is as it was. That is exactly what a linked list operation looks like. We are simply breaking off the chain to one music connection from the list. That is what a linked list operation looks like realistically. Also, a linked list is used to build a number of build a number of data structures like stacks and queues, and I believe even graphs. Now, for a linked list, there are three major types. There's a singly linked list in which each node points to another node and points to the other node till we get to the null. The null is the last value in our linked list. So after the last value, and there is no other value that points to, we use null as a representation. And just for terminology, the first node in our linked list is called the head. So in a singly linked list, the node points to another node and points to the next node. There's a doubly linked list where each node points to the next node, but the next node also points back to the previous node. So we have access to what we previously accessed. So it's like a two-way street for the doubly linked list. For the cyclic linked list, what we have now is null is pointing back to the head. So in the cases of singly and doubly linked list, they're not pointing back to the head. Null is just null. But in the case of a cyclic linked list, null points back to the head. In the case of a doubly linked list, we have the pointers not just going forwards but also going backwards. Now in this code, we are examining, constructing, and building a singly linked list. Now let's jump into the code and see what constructing a linked list in code looks like. So the first thing that we want to do in our code is we want to define the structure of our node. So we're going to be using a class function, obviously. So call that node, define the constructor object, pass it the value, and then define the structure of what our node should look like. So every node should contain a value that is going to be equal to the value of our parameter, and it's going to have a pointer. Recall that pointer that we talked about. Each node has a pointer pointing to the next value. Right now it's pointing to null because we do not have any value that it's pointing to. After creating our node class, let's go ahead and create our linked list class. Now this is our linked list class, and we also want to define some objects that each should have. So we want it to have an head, obviously. So the head is the beginning of our linked list. If you recall the terminologies that we used, the first node is called the head. The last node is always going to be null. So our node, we can just as easily create a new node and then initialize it with null because we have no value at this point. And we also want to keep track of the size of our linked list, and at this point it's going to be 0. So the first thing we want to do is we want to write our insert method. So before we continue with the insert method, I actually want to log a linked list to show what that looks like. So we have lists. Let's call our linked list class, and now let's log a list. So when we log the list and I run this in the console, we can see the structure we are currently working with. We have an head. The head is a node. The node has a value which is currently null because we set it as null, and the tag has a next value that's also pointing to null. So literally the node is all we have. If we made this a value of 5, it's going to move that and run it again. Now we see that we have a head node with a value of 5, and next is pointed to null. Our size is 0. So now let's continue with our insert method. So the first thing we want to do is with our value, we want to make it a node class. So we're going to make a new node, make that 5, and we are going to check if head is actually null, but let me assign that to a variable called current, but I'm going to call that curr, but it's supposed to mean current. So if current is not null, or if current is null rather, what we want to go ahead and do is we want to set our head to be this new node, because it basically means that we do not have any value. Our head is null. That's what this means. Otherwise, that means our head is not null, and we want to add this new node to the end of our linked list. So we're going to say that while current is not null, we want to go ahead and keep on moving. Basically, we're just moving and moving. So it's like saying, okay, we have this linked list. We get to the first value, it is not null. Let's say there's a value of 5, we go to the next one, there's 5. So until we get to the point where the next value, not current, but where the next value is not null. So if we have values, we do not want to obviously overwrite our values until we get to the point where we have no value. Then we want to set that we want to set current or next to be equal to the node value. And let's also remember to increment our size. Recall we are tracking here. So by incrementing, we have our else, we have insert. So we want to increment size here. Also, we're not using value. We should be using value, not add coding 5. Now let's try to insert. So we have list or insert. Let's insert 5. Let's insert 0 and -2. Okay, let's do -2. Should we do one more? Let's do a 10 or a 12. All right, now let's run that. So now when we run our code, we can see that we have a head node whose value is null. That is not right. Our value is not null. So we have a head node whose value is null. That's not right. The value should not be null. And the error is coming from line 18 where we are checking if current is null. Current is not necessarily null because we can see from the logs that this is what it should look like. It is a node. So we want to check if the value is null, not if the item itself is null. It's only going to be null if it's the last element in our linked list where the last element is just the value of null and has no next pointer. Now let's clear out our console and run it again. And we can see that our head node has the value of 5, which is the first item we're pointing to. Then the next links to another node with a value of 0, and everything is kind of like hidden now, but we get the idea of the value is 5, the next value is 0, and we can see that the size is rightly 4. Let's work on a print statement that shows us all the value. I do like to keep these to kind of like see how the linked list is linked programmatically to see that the next links another object or another linked list rather. But if we want to get out all the value, we can write another method. We call it print list. Let's again access the head. The head is always going to be the start from which we can loop through our entire linked list. Let's give a value of result, which is going to contain our values. While current is not equal to null, we want to go ahead and add the values of the current values. Then let's also just make sure to add a nice looking marker and increment that so we don't have an infinite loop. At the end of our statement, we want to make sure to return results. Now let's add that also to the list of methods. So we have print list. So now when we run this, let's clear out our console and have a good look at this. So we can see that we have 5, 0, -2, and 12. And 12 is not pointing to anything. Let's just make that be null. Let's run that once again. And you can see the values that we are inserting and our linked list structure. So I can just go ahead and comment out our linked list structure for now and continue to write our functions. So we can talk about the complexities before we continue with the different method that we want to write. So insert basically takes a time complexity of O of n because we are traversing the entire linked list regardless of the size. So that's an O of n. And for the space, we are not using any extra memory. And so this is a constant space. Now we can see inserting values. This is always going to insert values at the end of an array. What if we want to insert value at a specific point, at a specific point in our array? So let's write that method and call it insert at. So we would be our method is going to take in two arguments, a value that we want to create and also the index that we want to insert it at. So as usual, the first we want to do is create a node from the value that we are given. And we also want to make sure that the index is valid. So if our index is less than 0 or the index is greater than our current size, then we don't have access to that because it literally doesn't exist. If our linked list currently has a size of 4 and they're asking us to and we are being asked to insert the value at an index of 16, then that doesn't exist. We don't have a length as large as that. So we want to console.log some sort of error to and say that invalid index access, and we also want to make sure to exit that code and return it. Also, let's get some access to our head if it exists. So if we're asked to insert, if the index is equal to 0, so for instance we want to insert a new value at index 0, so what we want to do is we want to set node, this dot head is going to be the new node that we just created because we want to insert at the point of our head and our head is our first index. Then we want to make sure to also point node.next to current.next so we do not lose track of the other elements that we have or the other values that we have. So for instance, if we replace 5, if we want to insert a value 6 at index 0. So 6 is going to take index 0, but no, recall that all of our linked lists are connected by these little chains, these links, right? So we want to make sure that we connect the next pointer of our new node, which is 6, to what current rather. So we want to make sure that now 6 points to 5 such that 5 is index 1 and 6 is index 0. So now let's continue. Otherwise, if we are not asked to, if we have any other index but 1, what we want to do instead is have some sort of count. Let's start with 0. So we want to define another variable called previous to kind of keep track for us, and you would see what I mean in a moment. Now we want to traverse our linked list. So while count is less than the index that we want to keep track of. So we want to check while count is less than the index, we want previous to be equal to the current value that we are on, the current index, and then we also want to make sure to increment current because that's the only way we can actually loop through by literally incrementing this. But we want to keep track of where we currently are. So when we get to the index, previous is the guy that keeps track of the current position that we are in our linked list. And we also want to make sure to increment our count. The count acts as a dummy number to help us keep track of our current index. Now, when we get to the point where count is now equal to index, so we've gotten to the element that we do want to replace or insert at. Now, previous, which is our current, is going to point to our node, and our node the next And our node.next is going to point to the current element. But recall that from here, the current element is actually pointing to the next item. So now when we insert a value, so let's go here and say we want to insert 4 at index 3. So let's do index 2 instead. So what we expect is that 5 is index 0, 0 is index 1, minus 2 is index 2, but we want to replace it with 2, and then 2 will not then point to minus 2. So 2 is going to be between 0 and minus 2. That is what we expect of our code. So now when we run this, we can see that, okay, we ought to do insert at, not insert. So insert at. So when we run this once more, we can see that 4 is in between 0 and minus 2. Now the same complexities work for insert as insert at, because it is possible that we do traverse the entirety of our linked list and the space complexity is constant. So we have that to be O of 1. And so this print list where we are I want to say recovering, so I'm just going to stick with it, where we're recovering all of the values in our linked list and outputting it in our console, also takes the time complexity of O of n, because again we are traversing the entire length and we're not using any extra space, and that is results just a variable, so that's a constant space. Now finally, let us work on the delete function. So when we want to delete a value at a particular index, so our the only parameter we're taking is going to be the index, and we also want to make that check if index is less than 0, or if index is greater or equal to the exact size, because you do know that index of most elements in our programming language starts from 0. So the last size doesn't count because the index is going to be a -1. So that's why we're using the greater than or minus the size. Let's go over here and copy this code that we use for. So we have the invalid index access, and then we are also returning. So before, in fact, before we continue with our delete function, why don't we play around with what we did with our insert? So insert, we have, let's try to insert 40 at index 20. Recall that index 20 does not exist. So when we run our code, we want to see that there is invalid index access. There is invalid index access. And if we try to, again, what value is less than 0? We have -1. So when we run that, we again see that there is an invalid index access. How about we try to insert 40 at index 0, which is essentially the first item. Let me delete this log, run this again. We see that we have 40 being the first element in our linked list and then pointing to the head and everything else. So basically that is how our code runs on and on. Now let's go back to our delete function. So in our delete method, we are checking the edge cases in case we have an invalid index. Now we want to go ahead and also keep track of our head, store it in our current variable. We also want to go ahead and loop through. Actually, we want to check though, what if head is the index that we were asked to remove? So if the current index is 0, then we want to go ahead and set our head to current.next, effectively cutting off our current head. Otherwise, we want to loop through our current. So while also we want to use count to keep track of our current index. So let's make that 0. Let's also keep track, store our current value in another variable called previous. So while count is less than index, and I need to format this because it's making me a little icky. All right, cool. So while count is less than index, we want to store what we have in current into previous because current is going to be moving, right? So we want to store that, make that current on next. Let us, not next sibling, next. Let us also not forget to increment our count. And whenever this condition is true, that count is already equal to index, we want previous dot next to be current dot next. So we are cutting off current completely and just setting the next value of previous to current dot next. And we also want to make sure to decrease our size. So when we insert at, we didn't increment our size. We ought to have done that. So once we increment size, let's be sure that we're keeping track of that. It's quite important. And for delete, we want to be sure to also decrease the size of our linked list. Now let's give that a quick spin. So when we list or delete, we want to delete the index at want to delete the node at index 0. So that should be 40. Now when we run this, we can see in our console that 40 is gone. We now have only 5 and 0. So let me remove. Okay, let's delete more items. Let's delete 0, 1, and 3. Okay, let's remove this one so we're not confused about what's going on. Clear our console. Let's try to delete the third item, and we can see that we should have previously had 40, 5, I believe, 0, no, 4, 4 between 4 should have been between 0 and -2, but we are essentially removing 4. So 4 is no longer index 2 since 40 became index 0. So 4 is essentially the item at index 3, and that's what is being deleted. So for complexities, we have basically the same complexity. We are going to be traversing the entire list. So it's an O of n operation, and we're not using any extra space. So that's a constant space. Now, I would advise that you practice this on your own and get familiar with it. Also, there are some linked list questions, some easy questions that I believe would also be a good way to practice this structure that you've learned. So I would typically advise, okay, now you've created your own linked list. Why not try to work on some of those questions? Maybe one. We also have some answers on this channel. And then maybe tomorrow to kind of give yourself some spaced repetition, or the day after, go back to trying to create it again. And then it becomes easier to understand what a node is, what a tail is. If you see the question, some of the terminologies should no longer be completely daunting, as well as the structure that you see, because it's typically different from the regular array structured algorithms. I hope you found this helpful. If you did, please give it a like, comment, subscribe, all of those good stuff to encourage me, I guess. And I'll see you in the next video. Thank you so much for watching.